Now that we understand how to use the definite integral to figure out the area under a curve, we can talk about the fundamental theorem of calculus. So our definite integral, the integral from a to b of f of x dx, is giving the net area over the interval of integration. And from our notation back when we did our antiderivatives, it says that this is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. So here we want to evaluate the definite integral from 1 to 5 of 1 minus x dx using our fundamental theorem. So the function f of x is equal to 1 minus x. We need to find the antiderivative f of x. So using our antiderivative rules, I know this is going to be x minus 1/2 x squared plus some constant c. They didn't give me any value, so I don't know what c is, but when I put them into the formula, the c's are going to drop out. So my integral is equal to f of 5 minus f of 1, so I need to find f of 5, which is 5 minus 25 over 2, plus c. And then combining like terms, 5 would become 10 halves, so 10 halves minus 25 halves would be negative 15 halves, plus c. Then I also need to find f of 1, which is 1 minus 1/2 plus c, which is just equal to 1/2 plus c. So now I can do my integral from 1 to 5 of 1 minus x dx, which I know is equal to the antiderivative f of 5 minus the antiderivative of f of 1. So I have negative 15 halves plus c minus 1/2 plus c. So my negative 15 halves minus my 1/2 is negative 16 halves. I have a positive c. When I distribute the negative, it's minus c, so those are gone. So this area is equal to negative 8. Okay, here we're evaluating the integral from negative 2 to 1 of 2x dx. So again, f of x is the 2x. We need to find our antiderivative, which is x squared plus c. So then I evaluate the antiderivative at 1, and I get 1 plus c. I evaluate it at negative 2, and I get 4 plus c. So then to evaluate my actual integral from negative 2 to 1 of 2x dx, I do the antiderivative evaluated at 1 minus the antiderivative evaluated at negative 2. So I have 1 plus c minus 4 plus c, and I get negative 3. So now that we can evaluate our integrals a little quicker using our antiderivative rules, we have what we call the area function. So the area function a of x is equal to the integral from a to x of some function f of t dt, where a is less than or equal to x, less than or equal to another value b, so it has to be, x has to be greater than a. And notice t here is just, it's a dummy variable, because we're just plugging it in, and when I do this and evaluate this, I'm just going to get f of x, okay, the antiderivative. And so a prime of x is the derivative with respect to x of the integral a of x f of t dt. So my area function is the antiderivative of the function f. So kind of weird notation, so let's take a better look. So here they said the area function is equal to the integral from negative 1 to x f of t dt, and f of x is the integral from 3 to x of f of t dt. So my area function, if I want to find a of 3, so 3 is what I'm plugging in for this x value here, that means I'm looking from negative 1 to 3. So I'm looking at this area here, which I see is 27, but it's below the x-axis, so this is equal to negative 27. The next one, f of 5, now I'm looking at the f function, but it's still the area function, and I'm only looking from 3 to 5. So that's that little green area, and they told me that area is 3. And a of 9 goes from negative 1 all the way up to positive 9. So it includes the two salmon colored and the green. So I know that's negative 27 plus 3 plus, minus the 35 plus the negative 35. So a of 9 is equal to negative 59. Now if we change the question, this is finding our net area. Right here in all of these we found net area. If we want to find the total area, so that would include areas above and below, I would have to take the absolute value of each. So here I'm looking at essentially a of 9, but the absolute value would tell me it's 27. Absolute value of negative 27 is 27, plus 3, plus 35. So this area would be 65. So that's our difference between net area and total area. So here we want to find the net area and the area, or total area, for the region bounded by y equals 5 sine x on the x-axis from the interval negative pi over 2 to pi. Well, here it helps to know where sine is positive and negative. So if we sketch our sine curve, sine starts at 0, 0 in the middle, 0 at the end. It goes up to 1. In this case, we're going up to 5 because our amplitude has changed, and it's going to go down to negative 5. But it said we're going all the way to the halfway, negative pi over 2, so that's here. So the regions we're looking at are right here. And we're only going up to pi and up here. So those are our boundaries, from here to here. So now when we're trying to figure out our area, we know that this piece is negative, this piece is positive. So we're going to need to take note of that when we find our total area. But to get our net area, we're doing the integral from negative pi over 2 to pi of 5 sine x dx. So my antiderivative here is going to be 5 cosine x times a negative 1, because the derivative of cosine x would be negative sine x, so we have to make it a negative. And then we're evaluating that from negative pi over 2 up to pi. So I have negative 5 times the cosine of pi minus negative 5 times the cosine of negative pi over 2. So I have negative 5, the cosine of pi is negative 1, minus negative 5, the sine of negative pi over 2 is 0. And I get that the net area here is a positive 5. There's more above the graph than there is below the graph. Now, to figure out my total area, I would have to break this apart into pieces. So I would want to do the integral. So to find our derivative, I have to take the absolute value of this first region and add it to the second region. So I have the absolute value of the integral of negative pi over 2 to 0 of 5 sine x dx. And then I'm adding to that the integral from 0 to pi of 5 sine x dx. So when I take my derivative here, this is going to be negative 5 cosine x evaluated from negative pi over 2 to 0. And then I'm adding to that negative 5 cosine x evaluated from 0 to pi. So here again, these are absolute values. So negative 5 times cosine of 0 is negative 5. And then that's minus negative 5 times the cosine of negative pi over 2 is 0, so that's 0. And I'm taking the absolute value of that. Plus, over here, I have negative 5 times the cosine of pi is going to be positive 5. The cosine of 0 is 1, so I'm subtracting negative 5 times 1 is negative 5. So the absolute value of negative 5 is just positive 5. Plus, over here, 5 minus negative 5 is 10. So this total area, the net area, is 15. Now we can also take our area function to recognize if I'm taking the derivative of an integral. Now again, here's my t is my dummy variable, and I'm evaluating it up to x. This derivative simply becomes x squared plus x plus 1. Now the rule is the constant has to be at the bottom, the variable has to be at the top. So in this case, we want to still take the derivative of the integral from x to 5 of t squared plus t plus 1, so same dummy variable t, but my 5 and my x are in the wrong place. So now I'm doing the derivative of the negative integral from 5 to x of t squared plus t plus 1 dx, or excuse me, dt. So when I plug these in, it's just going to be the negation of x squared plus x plus 1.